Hello viewers, in today's class we are going to discuss one important and very conceptual problem from integral inequalities, right? So in this class we'll solve this very important problem in which we have to make use of one important inequality connecting two integrals, right? So let us first see the concept and then we can apply that concept to solve this problem. So here we are given this problem where we are given this integral 0 to 1 and the integrand is x raised to 4 sine inverse x dx is less than or equal to pi raised to p divided by q, where p and q are both greater than 0. Then we have to find the value of p plus q, right? So here what we will do, we'll solve this problem and then we'll find out this term, right? That is pi raised to p over q by making use of the concept, and then we'll compare the two results and then we'll find the value of p and q, and then the desired value of p plus q can easily be obtained. So let us first see the concept, right? Suppose we have two functions, say f of x and g of x, right? And f of x is greater than or equal to g of x for x greater than or equal to a and less than and equal to b, right? So if we have two functions like this, f of x is greater than or equal to g of x in this interval, that is from a to b, then we can claim that the integral from a to b f of x dx should be greater than or equal to the integral a to b g of x dx, right? So this is the integral inequality which is going to be used to solve this problem. So let us see this inequality by using a diagram. See, suppose we have here x-axis, here we have y-axis, right? And suppose this is f of x, this function is f of x, that is this curve is given by this function f of x, and suppose this is the function g of x, right? And here we have a and here we have b, right? Now see, for all values of x belonging to this interval, that is a to b, that is this interval a to b, this function f of x is always greater than or equal to this function g of x, right? So this inequality says that the area bounded by this function f of x, right? Because see, the definite integral denotes the area, right? So the area bounded by this function f of x within these two limits is always greater than or equal to the area bounded by this function g of x within these two limits, right? So this area, that is the integral a to b f of x dx, is given by this area, right? So this area is denoted by this integral a to b f of x dx, and this area, right, that is the area which is lying below this curve g of x. This area is denoted by this integral, right? So obviously the area that is a to b f of x dx is greater than this area, that is a to b g of x dx. We can also explain it like this. Suppose this is a, this is b, this is c, this is d, this is suppose e, and this point is f, right? then the area ABFE, right? The area ABFE is greater than or equal to this area, that is area DC DCFE, right? So this area is greater than or equal to this area, and this area ABFE is given by this integral, that is a to b f of x dx, and this area is given by, that is DCFE, is given by a to b g of x dx, right? So we'll use this property to solve this problem. So now let us start with this function, that is sine inverse x, right? Now from the concept of inverse trigonometric functions, we know that the principal value branch of sine inverse x, it belongs to this interval, that is minus pi by 2 to pi by 2, right? So sine inverse x belongs to this interval, right? Now see, when we take the limits from x is equal to 0 to 1, then sine inverse x should be less than or equal to pi by 2, right? So this is for x greater than or equal to 0 but less than or equal to 1, right? So whenever we have x lying between 0 and 1, then sine inverse x is less than or equal to pi by 2, right? Because from this principal value branch, we know that sine inverse x, it belongs to this interval, that is minus pi by 2 to pi by 2, and between minus pi by 2 and pi by 2 we have the point x is equal to 0. So now we'll take this inequality to move further, right? Now see, here we have x raised to 4, right? And for x lying between 0 and 1, x raised to 4 is always a positive quantity, right? Because x raised to 4 is always a positive quantity whenever x goes from 0 to 1. So we can multiply this inequality throughout by x raised to 4, right? So what we will get, x raised to 4 sine inverse x, and then less than or equal to x raised to 4, and here we have pi by 2, right? So now we have obtained an inequality which is similar to this one, right? Because f of x is greater than or equal to g of x. So now comparing this inequality with this one, we can take this function as f of x and this function as g of x, right? So f of x is our pi x raised to 4 divided by 2, and g of x is our function x raised to 4 sine inverse x. So now we can write this inequality as f of x greater than or equal to g of x. So f of x is greater than or equal to g of x. So we can now apply this inequality, right? And a is our 0 and b is 1, right? So now taking the integral of these two functions from 0 to 1, we have 0 to 1 f of x dx is greater than or equal to the integral from 0 to 1 g of x dx. So now we have 0 to 1 f of x is pi x raised to 4 over 2, and here we have dx, and then we have 0 to 1 and g of x is x raised to 4 sine inverse x, and here we have dx. So now if we take this integral as I, then here we have this integral equal to I, right? So we have I that is less than or equal to 0 to 1, and we have pi x raised to 4 divided by 2 dx. Now we can easily solve this integral. So this integral is pi by 2. Taking pi by 2 outside the integral, we have 0 to 1 x raised to 4 dx. And then we can write pi by 2. The integral of x raised to 4 is x raised to 5 over 5. Limits are from 0 to 1, right? So now we can write it as pi by 2, and here taking the limits, and we'll take the difference. So we have 1 raised to 5 over 5 minus 0 over 5, and that is equal to pi by 2 times 1 over 5, and that is I less than or equal to pi over 10. So now we have obtained this inequality. That is, this integral is less than or equal to pi over 10. Now see, in the given problem, we are given that I is less than or equal to pi raised to p divided by q. Now, if we compare these two results, then here we have pi raised to 1, because here we have only pi, so we can take it as pi raised to 1, and q is 10, right? So comparing both these results, we have p is equal to 1, p is equal to 1, q is equal to 10. So we have to find the value of p plus q. So p plus q is simply 1 plus 10, that is 11, right? So this is how, by making use of this concept, we can solve these kind of problems. Hello viewers, in today's class we are going to discuss yet another important and very conceptual problem from integral inequalities, right? So in this class we'll solve this problem where we have 0 to 1 e raised to 2x cos x dx is less than or equal to p times sine. Here we have the hyperbolic sign, so we have hyperbolic sine of q. We have to find e raised to pq, where p and q are greater than 0, right? So here we are given an integral inequality in which this integral, that is 0 to 1 e raised to 2x cos x dx, is less than or equal to p times the hyperbolic sine of q. Then we have to find the value of this expression, that is e raised to p times q, where p and q are greater than 0, right? So let us start. So here we are going to find the application of one important integral inequality, which says that if we have two functions, say f of x and g of x, right? Suppose we have two functions, f of x and g of x, and f of x is greater than or equal to g of x in the interval, that is x greater than or equal to a but less than or equal to b, then the area bounded by this function f of x within this limit, that is a to b, is always greater than or equal to the area bounded by this function or this curve g of x between these 2 points a and b, right? So then we can write the integral a to b f of x dx should be greater than or equal to the integral a to b g of x dx, right? So in our earlier video we have already explained this inequality in detail, right? So here we are going to use this concept to solve this problem. So let us take this integral as I, right? So here we have I is equal to 0 to 1 e raised to 2x times cosine of x dx, right? So now this inequality reads as I less than or equal to p times the hyperbolic sine of q, right? So now we are given this inequality, and with the help of this result, we have to find the values of p and q, and then we can find out the value of this expression, that is e raised to p times q. So now let us start with this function, that is the cos of x. So we know that in trigonometry, cos of x is less than or equal to 1 whenever x belongs to the interval 0 to 1, right? So here we'll start with this inequality, that is cosine of x is less than or equal to 1. Now see here, we have this term e raised to 2x associated with cosine of x, right? So to get e raised to 2x with cosine of x, what we will do, we'll multiply this inequality throughout by e raised to 2x without disturbing the direction of the inequality. Why? Because we know that the exponential function is always greater than 0 for all x belonging to the set of real numbers, right? So e raised to 2x is always a positive quantity for all values of x belonging to the set of real numbers. So what we will do, we'll multiply cos x and 1 by e raised to 2x so that we can get this term, right? So we have now e raised to 2x cos x, and here we have 1 times e raised to 2x, so this is e raised to 2x, right? So now we have obtained an inequality which is similar to this one, right? So whenever we encounter these type of problems, our first aim is to get an inequality which is similar to this one, that is f of x is greater than or equal to g of x, or in other words we can say that we have to form, or we have to frame an inequality which gives us the function f of x and g of x, right? So what we will do, we'll now take this e raised to 2x as f of x, and e raised to 2x times cosine x as g of x, right? So now see what we will get. Here we have g of x, and now this is less than or equal to f of x, right? So we can also write this inequality as f of x greater than or equal to g of x in the interval 0 to 1. So a is 0, b is 1, right? So a is 0 and b is 1. So we have obtained e raised to 2x cosine x is less than or equal to e raised to 2x, or in other words we can also write it as e raised to 2x is greater than or equal to e raised to 2x cos of x, right? So e raised to 2x cos x is gx, and e raised to 2x is f of x. So we have f of x greater than or equal to g of x, right? So whenever we come across with these type of problems, our first aim is to form or get an inequality which is similar to this one, so that we can assign, or we can take the function f of x and g of x out of the inequality. So now we have fx greater than or equal to g of x. So we can now apply this inequality, that is integral of f of x from a to b. So here we have a 0, b is 1. So we have 0 to 1 f of x dx should be greater than or equal to 0 to 1 g of x dx, right? Now f of x is e raised to 2x. So we can now write 0 to 1 e raised to 2x dx greater than or equal to 0 to 1. G of x is e raised to 2x cos x, right? And now this integral is I. So for simplicity we can now write the integral, this integral can be denoted by I. So we have 0 to 1 e raised to 2x dx is greater than or equal to I, right? So we can write now I, this is less than or equal to 0 to 1 e raised to 2x dx. So I is now e raised to 2x over 2, and the limits of integration are from 0 to 1. The integral of e raised to 2x is e raised to 2x divided by 2. So now we can write I less than or equal to, here we have half, taking half outside and then substituting the limits. So we have e raised to 2 times 1 is e square minus, and taking x is equal to 0, here we have e raised to 0, right? So I is less than or equal to half e square minus 1, because e raised to 0 is equal to 1, right? So now we have obtained another important result, that is this integral, that is 0 to 1 e raised to 2x cos x dx is less than or equal to a half e square minus 1, right? So this is another important result related to this integral. But in this problem, we have to express this result in this form, that is p times the hyperbolic sine of q, right? So here we'll use the definition, that is hyperbolic sine of x is given by e raised to x minus e raised to minus x over 2, right? So this is the definition of a hyperbolic function of sine of x. So here if we take x is equal to 1, what we will get, sine, here we have sine h1, that is hyperbolic sine of 1, that is e raised to 1 minus e raised to minus 1 over 2. So this is e minus 1 over e divided by 2. So e square minus 1 over 2e, right? So hyperbolic sine of 1 is equal to e square minus 1 over 2e. So now what we will do, we'll take this e to this side, right? So e times the hyperbolic sine of 1 is equal to half times e square minus 1, right? So now we can substitute the value of half e square minus 1 in this relation, right? So now this relation becomes, if we replace this integral by I, we can write I less than or equal to half e square minus 1, which is equal to this expression, that is e times hyperbolic sine of 1, right? And see, here we are given that this integral I is less than or equal to p times the hyperbolic sine of q. So now if we compare these two results, then we can easily see that P is equal to E and Q is equal to 1, right? This is a very important problem. P is equal to E and Q is equal to 1, and P and Q are obviously greater than 0. E and 1 are greater than 0, right? And we have to find the value of E raised to PQ, right? So P is E. So we have E raised to E times 1, that is E raised to E, right? So this is how we can find out the value of this expression using this integral inequality, right? So viewers, by making use of this important integral inequality, we can solve these kind of problems.